Hi, welcome back. We'll move on to the topic of integral closures. The next topic is this topic of integral closures. And before I move on to this topic, I'll review a few facts from abstract algebra, the ring theory and module theory that you might have learned in a course on abstract algebra. So recall some facts. From ring and module theory. So these are just facts that I'm recalling. Suppose you have an inclusion of rings, and let's just say you have an inclusion of domains. Say R1 inside R2. If you have an inclusion of domains this way, then this turns R2 into an R1 algebra, and we say R2 is finitely generated, and just as in the previous lecture, I'll abbreviate finitely generated by f dot g dot. So R2 is a finitely generated R1 algebra if we have a surjection of R1 algebras So you have this polynomial ring over R1, infinitely many variables that surjects onto R. Okay, so for some finite natural number, okay, and similarly, if you have 3 domains and you have a sequence of inclusions, say R1 inside R2 inside R3, so you have an inclusion of domains this way, then again R3 is an R2 algebra, and since R1 is inside R2, R3 is also an R1 algebra. And suppose you have that R3 is finitely generated as an R2 algebra. Again, what this means is there is a surjection of R2 algebras if it's a surjection of R2 algebras, it will also be a surjection of R1 algebras. So you have R2, this polynomial ring infinitely many variables over R2 surjects onto R3. Let's call this equation star. So we have a sequence of inclusion of domains R1 inside R2 inside R3, and suppose R3 is finitely generated as an R2 algebra, and similarly if R2 is finitely generated as an R1 algebra, again same similar conclusion. So it just means that there is a surjection of R1 algebras where you have this polynomial ring in say y1 up to yt. These t variables surjects onto R2. Okay, and let's call this star star. So if you have that R3 is finitely generated as an R2 algebra and R2 is finitely generated as an R1 algebra, we have the sequence of inclusions R1 inside R2 inside R3, then the conclusion is that R3 is finitely generated as an R1 algebra. Okay, and the idea is just we have this equation star and equation star star, you just combine these two equations suitably. So idea is just to suitably combine star and star star. And then you end up with an surjection of R1 algebras of the form use the variables y1 up to yt and x1 up to xm to get the surjection onto R3. Okay. But in fact, you can sort of repeat this argument and use an inductive argument. So if you have an inclusion of domains, not just R1 inside R2 inside R3, but let's say you have R1 inside R2 inside R3, and you have a long sequence, say inside all the way up to Ri to Ri plus 1, and all the way up to say Rn minus 1 into Rn. And so again, each Ri plus 1 is an Ri algebra, but furthermore, suppose that each Ri plus 1 is a finitely generated Ri algebra for all these Ri's. Then we can inductively argue, or using induction we can conclude that Rn is a finitely generated R1 algebra. Okay, so that was the algebra structure. But similarly, if you have an inclusion of rings, you also have a module structure. So suppose similarly we have an inclusion of domains. R1 inside R2. This turns R2 into an R1 module. Okay, and similarly we say R2 is finitely generated as an R1 module if there exists a surjection of R1 modules of the form R1 to the m surjects onto R2 for some natural number m. Okay, and just as we argued earlier, with the algebra structure we can carry over a similar argument for the module structure. Sorry. Just as earlier, if you have a sequence of inclusions of domains, with each Ri or Ri plus 1 being finitely generated as an Ri module, then you can conclude that Rn is a finitely generated R1 module. Okay, so that concludes the collection of facts from ring and module theory that you might have seen in an abstract algebra course. So we'll come back to our course now. So what's the setting? We have a domain A that sits inside a field. Let's call it L. Okay, so I want to make a definition. So I'll call it OA. It's the set of elements of L that are integral over A. Okay, it's just a definition. I'm considering a set which consists of all the integral elements, all the elements of L that are integral over A. So it's just a set a priori. But the next proposition is that this set has some structure. It's in fact a ring. Okay, and so what we have to show is that if you have two elements, beta 1 and beta 2 in OA, the essential idea is that we need to show that the sum belongs to OA and the product also belongs to OA. Okay, so we'll start by showing that. And how do we do that? So you look at A adjoint beta 1 and beta 2. So this is the smallest subring of L containing A, beta 1 and beta 2. I want to get a sequence of inclusions of domains just as I've been discussing so far. So we have A, and then it contains A beta 1, or it's contained in A beta 1, and this is contained in A beta 1 beta 2, and everything is sitting inside L. Okay, so the thing in the middle, A beta 1, let me just call it A1, and the next term, A beta 1 beta 2, which is my B, I'll just call it A2 as well. So A2 is A1 adjoint beta 2. And again, A1, just to recollect, is the smallest subring of L containing A and beta 1. Okay. So now what do we have? Since beta 2 is integral over A, it belongs to this OA, so it's integral by definition. But A sits inside A1, so what that means is beta 2 is integral over A12. So why? Beta 2 satisfies a monic equation over A, but it's a monic equation over A and A sits inside A1. So beta 2 satisfies a monic equation over A1 as well. Okay, so what we have is that beta 2 is integral over a1, and so by proposition 1 from the earlier lecture, what do we have? We have that a1 adjoint beta 2 is finitely generated as an a1 module. Okay, but similarly, we have beta 1 is integral over a, and again it's by definition because beta 1 belongs to this OA, it's integral, and thus by proposition 1 from the earlier lecture, a beta 1, which is what we called a1, is finitely generated as an a module. Okay, and so again, just to recollect, thus we have a sequence of inclusion a inside a1, inside a2, with a2 a finitely generated a1 module and a1 a finitely generated a module. And so this implies that a2, which is a beta 1 beta 2, is finitely generated as an a module. Okay, but a adjoint beta 1 beta 2 is a ring So what we have is that beta 1 plus beta 2, that's an element of this ring. So when you multiply it with the subring a beta 1 beta 2, it still sits inside a beta 1 beta 2. And similarly, beta 1 times beta 2, that's also in this ring. So when you multiply it with any element of this ring a adjoint beta 1 beta 2, you still land inside a beta 1 beta 2. Okay, and so take M to be a beta 1 beta 2, and what we've shown is that again by using proposition 1 from our earlier lecture, beta 1 plus beta 2 times dot M sits inside M, beta 1 times beta 2 dot M sits inside M. And since we have these inclusions, this shows that beta 1 plus beta 2 and beta 1 times beta 2 are integral over A. And thus by definition, beta 1 plus beta 2 and beta 1 times beta 2, they both belong to OA. Okay, so this essentially completes the proof. So this shows that OA is a subring of L. Okay, and I'll just make a note that OA is the set of all elements of L that are integral over A. So I'll just note that A sits inside OA. Okay. Okay. So the next question. So can you repeat this procedure in L? So I started with a ring A. I constructed OA, which was the set of all elements that were integral over A. Now can I repeat this procedure again? So can I look at OOA, where this O subscript OA is the set of all elements in L that are integral over OA. Okay, so in fact we'll show that we can't repeat this procedure. So we'll show that OA is in fact O subscript OA, because this is what we are heading towards next. So proposition before that, suppose you have an inclusion of domains A sitting inside B sitting inside C. And let's just suppose that they all sit inside some common field, as we've been supposing. So let's call that common field L. And the property is that C is integral over B and B is integral over A. Okay. So just as earlier, what I want to show is that this property of being integral is also transitive. Okay, so the conclusion of the proposition is that C is integral over A. Okay, so what's the proof of the proposition? So you take an arbitrary element, let's call it gamma in C. And what do we want to show? We want to show that gamma is integral over A. So gamma is in C and C is integral over B. So gamma satisfies a monic polynomial over B. That is gamma to the n minus 1 plus bn minus 1, gamma to the n plus bn minus 1 gamma to the n minus 1 plus so on and so forth, b1 gamma plus b naught equals 0 for some of these coefficients bn minus 1, b1, b naught in B. Okay. Now instead of considering the whole ring B, let's just consider a subring of B with these coefficients A adjoin B naught, B1 up to Bn minus 1. Now what this equation in this blue box tells us, is that in fact gamma satisfies a monic equation over An. What I have is that gamma satisfies a monic polynomial over B. I write down a monic equation, I collect all the coefficients Bn minus 1 up to B1 and B naught, I adjoin that to A. So what I in fact have is this sort of stronger statement that gamma satisfies a monic equation over An. It's a more precise statement. So what does that mean? Again, by proposition 1 from the earlier lecture, An adjoint gamma is finitely generated as an An module. And now I just want to define some rings. So I define AI to be A adjoin B naught all the way up to Bi. And just note, what that means is that AI plus 1 is AI adjoin Bi plus 1. And just as we've been arguing so far, since these Bi's or Bi plus 1 belongs to B, it is integral over A, that is bi plus 1 satisfies a monic equation over A, but A is contained in this AI. So bi plus 1 satisfies a monic equation over AI, and again by proposition 1 of the previous lecture, what this means is that AI adjoint bi plus 1 is a finitely generated AI module. Okay, so again we have a sequence of inclusions, A inside A naught, inside A1, so on and so forth, AI inside AI plus 1, so on and so forth up to AN, inside AN adjoint gamma, where this A naught is A adjoint B naught, A1 is A naught adjoint B1, and so on and so forth. AI plus 1 is in fact AI adjoint BI plus 1. And the property of the sequence of inclusion of domains is that where each ring is finitely generated as a module over the previous ring in the sequence. Okay, so again by this transitive property we have that A and gamma is finitely generated as an A module. And once again, since A and gamma is a ring, what do we have? We have that gamma times A and gamma still sits inside A and adjoint gamma. And once again, now if we choose our module to be A and gamma, this is a finitely generated A module, and again by proposition 1 of the previous lecture, we have gamma is integral over A. Okay, so this completes the proof of this proposition, that being integral is a transitive property. So the corollary of this proposition, let's call it corollary 4. So I have OA and I have O subscript OA, these are equal. Okay, so let me just remind you that here OA is the set of elements of L that are integral over A, and OOA is the set of elements of L that are integral over OA. Okay, so the proof of the corollary is just, so note we have a sequence of inclusion, A sitting inside OA, sitting inside OOA, and everything sits inside L, with OA being integral over A and OOA being integral over OA. And so by the previous proposition, so thus by proposition 3, using this transitive property of being integral, what we have is that OA is integral over A. Okay, so that means every element of OA is integral over A. But if you're integral over A, you must belong to OA. So again, by definition, this OA must sit inside OA, since OA is the set of all elements of L that are integral over A. Okay, so we already have that OA sits inside OA, and now this previous proposition 3 allows you to show that OA sits inside OA. Okay, so thus OA equals OA. Okay, so that completes the proof of the corollary, and I'll end with a definition. So we call OA as the integral closure of A in L. And a ring A is said to be integrally closed in L if you do this procedure. So you take A and you compute OA. If A equals OA, then we say that A is integrally closed in L. And if you have a domain, we say that the domain is integrally closed if it is integrally closed in its fraction field. Okay. Thank you.